With the onset of planetary urbanization has come the age of mass consumerism and products that satisfy the desire for human convenience. We live in the plastic era where waste plastic is accumulating in all shapes and sizes in our natural systems. Plastic pollution across the Earth's surface is an undeniable indicator of the Anthropocene epoch. In 2018 alone, 359 million tons of plastic was produced. It is estimated that each year 8 million metric tons of plastic enters the oceans. This annual accumulation has resulted in 5 gyres or islands of plastic in the Earth's oceans. The largest of these islands is the Great Pacific Garbage Patch, which covers an area of 20 million square kilometers and is estimated to weigh 80,000 tons. This plastic in the ocean poses a variety of risks to ecosystems and species. Entanglement and ingestion kill thousands of marine animals each year. However, the breakdown of this plastic poses a greater risk with the biomagnification of micro and nanoplastics through the food chain. It is estimated that 8% of the Pacific Garbage Patch is microplastic, and this number is quickly increasing as particles continue to break down, placing greater urgency on getting the plastic out of the ocean. Currently, major initiatives exist around the world. However, most of the garbage collected in the past decades has been directed to landfills because of limited recycling infrastructure and technology. This project focuses on applications specific to remote Pacific Northwest coastal communities. Guided by ecological and indigenous values, this project intends to build restorative relationships with the natural environment and develop design interventions and fabrication strategies that consider the well-being of remote indigenous communities. Building off existing initiatives, this project attempts to provide opportunities to better recognize the true value of the ocean plastic and explore ways it can be utilized in a local architectural application. Remote coastal communities along the Pacific Northwest are generally sea-locked communities with populations ranging between 250 and 15,000 people. Many indigenous nations inhabit areas of the coast and have for thousands of years. Harvesting from the ocean and forests is common practice for coastal residents, making food security very susceptible to ecosystem collapse. Therefore, these communities have an invested interest in collecting ocean plastic and maintain an ethos of ecological stewardship. Validating the composition of ocean plastic was done through conversations with individuals actively involved in coastal garbage collection and published surveys completed by the Ocean Cleanup. Based on this research, a range of commonly found ocean plastics was determined. Commercial fishing equipment comprised of hard plastic floats, baskets, nets, and rope, and polyethylene foam blocks make up an estimated 46% of the plastic in the garbage patch. Building off of existing opportunities and assets in coastal communities, a collection process has been outlined. As a result of crashing fish stocks and the outsourcing of Canadian fish processing to China, several closed canneries and fish processing plants have been indefinitely closed. As well, industrial-sized fishing boats with carrying capacity above 100,000 pounds are highly underutilized on the coast. In addition, smaller vessels and helicopter-based infrastructure also exist. In the first scenario, plastic would be collected along the shoreline by local community members. This plastic would then be placed in large reusable nets and transferred to large barges via helicopter or marine vessel depending on the geographic location. In the second scenario, fishing vessels and barges will head out to predetermined locations of the garbage patch. These boats will collect the garbage, filling their own storage holds as well as that of the barges. In both scenarios, the plastic will be transferred to the refitted canneries where infrastructure to retrieve the plastic from boats, chip, sort, and manufacture the plastic will be located. This cannot be easily or efficiently completed by humans. Therefore, using current, highly sophisticated technology such as light frequency cameras that use infrared, X-ray, and ultraviolet light to determine plastic density and color down to particles 2 millimeters in size. Flotation, magnetic, and artificial intelligence are additional technologies that will be deployed to help with the sorting process. A list of parameters have been identified to guide the methodology and research. Considering the general affordances of plastic led to the exploration of generating an exterior wall treatment. West Coast building exteriors must respond to driving wind and rain, salty air, and an extremely humid climate. Wood-clad buildings often have major buildup of mosses and lichen. Of the plastics found in the ocean, high-density polyethylene has been selected as a viable resin to explore based on researched and tested characteristics. Dozens of samples have been generated using heat molds in a small toaster oven. Through this process, different combinations have generated samples that explore the variables of melting these different plastics. Interesting transparency opportunities have been seen with the high-density polyethylene plastic samples, as well as opportunities with the integration of other common ocean plastics such as netting or rope. Even the integration of shells collected on ocean plastic have been tested in samples. A building typology study was completed from a series of buildings on Haida Gwaii. Constraints and variables were analyzed, resulting in the determination that western red cedar is a common exterior cladding material in the form of a shingle or a shake. This exploration has informed the development of a recycled ocean plastic wall shingle for coastal environments. This typology study informed the dimensions and variations of the proposed shingle strategy. Fastening strategies have been based on the use of horizontal cables or strapping-like members attached to structure to mount the shingles to. A range of interlocking variations have been explored, offering weather-resilient exterior with some fastener-less installation options. One strategy slides vertically into the shingle below, while another slides horizontally into the shingle below. After testing these fastening strategies on the physical models, pros and cons of each were determined. The digital explorations have uncovered the parametric variation opportunities that this wall shingle strategy can employ. The width and length of the shingles can be varied, as well as the color and transparency based upon the recycled plastic used or added pigments. One of the goals of this digital exploration was to develop an efficient method of deploying the shingle strategy on any wall surface. This was achieved through the use of the digital tools Rhino and Grasshopper, where a script was generated to analyze any surface, curved or flat. Additional fastening strategies have been analyzed in an effort to generate the most seamless and efficient installation. The basic pseudocode driving the parametric variation divides the surface into horizontal lines, where these lines are then broken up into random or even divisions. The shingle is built from these line divisions into interlocking formations. Variations can then be deployed to this array, which vary shingle length, color, and transparency. These parametric variations can be deployed in subtle or extreme extents depending on the design intent. Additional explorations have gone into the fabrication capabilities of high-density polyethylene plastic. Beyond being moldable with heat, plastic samples have been tested with table and miter saw, drill, and the CNC. Each test produced satisfactory results that could be deployed in a fabrication process. Using adaptable molds, plastic could be melted into adjustable width and length dimensions, as well as curve requirements of the proposed surface. This would enable a mass customization process that could be shifted to many different project requirements. Through post-digital design, the potential outcomes and boundaries of this strategy can be explored and implemented in a contextual, virtual space. This has provided a better understanding of what is possible, what should be avoided, and greater insight into future iterations of the plastic wall shingle research. The proposed building is sited on Ellen Island, which is a small island in Rose Harbour at the south end of Haida Gwaii. This island is currently used for Parks Canada staff accommodation. This structure is intended to perform similarly to a canvas tent, meaning no defined air barriers exist, allowing fresh air to circulate while rain and wind are kept out. The structure respects the land, as the foundation of the structure does not contact the forest floor in an attempt to create the least amount of environmental disturbance possible. The building can be used as research buildings or private staff accommodation. Shingles and frame can be assembled and disassembled seasonally or moved to separate locations as required. The final artifact was constructed of recycled plastic and recycled building materials. Each shingle was baked using processes perfected over the course of this exploration. Each shingle holds a unique composition of collected plastic debris. The structure allows some light transmission while keeping the space totally private. The interior is reminiscent of a stained glass collage telling stories from the sea. High-grade cedar shakes require old-growth western red cedar in the Pacific Northwest. As these material sources dwindle and remaining old-growth forests are considered for protection, the plastic shingle offers a weather-resilient alternative that does not rot under humid conditions or crack when applied to a curved surface. This project attempts to shift the paradigm around exterior facade materiality, where ocean plastic waste can be diverted from the ocean and landfills and seen as a valuable product because of its material characteristics and embodied ethos of ecological repair of the Earth's oceans and indirect preservation of old-growth timber. This plastic embodies its own story of decades at sea, and each formed object maintains unique characteristics. There is also direct connection developed between the communities collecting this plastic and utilizing it. This project considers new ways of utilizing byproducts of the Anthropocene and harnessing it in ways that are ecologically regenerative, which in turn enables remote communities to continue to thrive.